Hello there and welcome back. In this lecture, we're going to be talking about the binomial distribution. It's section 2.6 in our notes. So far we've talked about the basic notion of probability, and then in 2.5 we talked about random variables and probability distributions just kind of generally. In this section, we're going to talk specifically about the binomial random variable and the binomial distribution. So it's a specific kind of distribution, and it's going to be very, very useful for us. So here's how we define a binomial variable. So first of all, an experiment is said to be a binomial experiment if the experiment is performed a fixed number of times, right? Each repetition is called a trial. The trials have to be independent. That is, the outcome of one trial is not allowed to affect the outcome of another trial. We've seen the term independence before, right? For each trial, there should be two mutually exclusive outcomes, which is another thing that we've seen before, right? Success or failure. And that's really kind of the big one, right? That's what makes a binomial experiment binomial is this condition right here, that there are two mutually exclusive outcomes. Hence the bi in binomial, right? And then finally, number 4 is that the probability of success has to be the same for each trial of the experiment. If those conditions all hold, then the experiment is called a binomial experiment. Now, we make a binomial random variable out of that by counting up the number of successes, right? So x will be the number of successes in a binomial experiment. If that's the case, then x is a binomial variable. So, for example, tossing a coin 3 times is a binomial experiment. If we count up the number of times we flip heads or the number of times we flip tails or something like that, then we have a binomial random variable on our hands. Some notation that we'll use when we're describing binomial distributions are these things, right? So P is going to be a lowercase p is going to be the probability of success, right? A lowercase q is the probability of failure. N is the number of trials. X is the number of successes. And P of x is the probability that capital X equals X, right? In other words, it's the probability that we have exactly X successes in our N trials. Going back to Q, right? P is the probability of success. Q is the probability of failure. Since you have two mutually exclusive outcomes, by the complement rule, it must be the case that Q is 1 minus P. So let's practice with these. Let's practice determining if we have an experiment that is binomial, and if so, then we'll practice identifying the number of trials, probability of success, etc. Part A says a player rolls a pair of fair dice 10 times, and the number of 7s is recorded. So to determine if that is binomial, we need to look through the list of these conditions here to see if all of those conditions are satisfied. We're going to roll a pair of fair dice 10 times, it says, and record the number of 7s. So yes, the experiment is performed a fixed number of times. So we're going to have 10 trials. The trials are all independent, right? When you roll a pair of fair dice, the outcome of your first roll does not affect the outcome of your next roll, okay? For each trial, there are two mutually exclusive outcomes, success or failure. Now, here's where you might start to struggle a little bit, because you might say, well, aren't there a whole bunch of different possibilities when you roll a pair of fair dice? And the answer is yes, but the way that this experiment was stated, right, it said that we were going to record the number of 7s. And so either you roll a 7 or you don't, right? And so that makes for success and failure. And then finally, the probability of success is the same for each trial of the experiment. Yeah, that's going to be the case, right? The probability of rolling a 7 is the same every time you roll the dice. So yes, this is binomial. Okay. Success in this case is rolling a 7. Number of trials was 10, so n equals 10. Probability of success, p. Okay, so here you should go back to section 2.2 when we first introduced sort of the basic notion of probability, and there was an example in that section where we listed out all of the possibilities when you roll a pair of dice. And if you look through that chart, you'll notice that there are 6 ways that you could roll a 7 out of 36 total possibilities. So probability of success would be 1/6. Probability of failure is the complement of the probability of success, right? If the probability of rolling a 7 is 1/6, then the probability you don't roll a 7 is 1 minus 1/6, right? Which is 5/6. Okay. And then we're also supposed to list out the possible values of the random variable x. Okay, well, let's see. You're rolling a pair of dice 10 times. It's possible that you never roll a 7, right? So it's possible x is 0. Or x could be 1, right? You might roll a 7 exactly 1 time or 2 times. Or it could be the case, and it would be very unlikely, but it could happen that you roll a 7 every time you roll the dice. So x could be as much as 10. But x can't be more than 10, right? Because you're only rolling the dice 10 times. And it can't be less than 0. And it also can't be a number like 3.7, all right? So those are the possible values of x. Okay, part B says three cards are drawn from a deck without replacement, and the number of aces is recorded. So this one is almost binomial because we have a success here, right? If you draw an ace, that's success. If you draw anything else, it's failure. And so it feels binomial in nature. However, the cards are being drawn without replacement. And that's an issue because that means that will violate the second condition, right? The trials are not independent. The outcome of one trial affects the outcome of another. Because the probability of drawing an ace on your second draw is going to be different from the probability of drawing an ace on your first draw, since you're not replacing the cards back into the deck. So this is not binomial. Okay, part C. A fair die is rolled 50 times, and the number that is rolled is recorded. Okay, this one is not binomial. The issue is that you don't have mutually exclusive outcomes here. You do have mutually exclusive outcomes, but there aren't two of them, there are 6 of them, right? So that's the issue there. Okay, part D. In a class of 30 students, 60% are female. The instructor randomly selects one student, records the sex of the individual, asks the individual to sit back down, and randomly selects again from all 30 students. This experiment is repeated 4 times, and the number of females selected is recorded. So this one would be binomial, and I would encourage you to kind of pause the video and think through that and make sure it meets all 4 of those conditions, but it does. Success in this case would be selecting a female, right? So we would say success equals female here. How many trials? So it looks like we repeated the experiment 4 times. Probability of success, well, 60% of the class is female, so the probability you select a female is 60%, right? 0.6. Probability of failure then would be the remaining 40 students. Okay, and then x, the possible values of x, well, you're going to choose 4 students. It's possible that none of them are female. That would be unlikely, but it could happen, right? Or maybe you get 1 female or 2 or 3. Maybe all 4 of the students you select are female, but you can't get five females if you're only selecting 4 students, right? So those are the possible values for x. Okay. Number 2 asks kind of a follow-up question. It says, we determined that some of the parts in example 1 were not binomial experiments. How might we adjust each one to make it binomial? So the ones that were not binomial were parts B and C, right? And for part B, the issue was that we were choosing the cards without replacement. So I think if we were just to replace the card back into the deck and then shuffle between choosing cards, then it would be a binomial experiment. So for part B, I would say replace the card and shuffle between draws. I don't know if that's the correct terminology, but that's but I think you understand what I'm saying. So that's part B. Part C was the fair die. So we were rolling a fair die, recording the number rolled. That one was not binomial because we didn't have 2 mutually exclusive outcomes, right? We had 6 mutually exclusive outcomes. So for part C, I think all we have to do is identify some outcome as being a success, right? So identify some outcome as success. For example, instead of recording the number that is rolled, we could record the number of times that we rolled a 2 or something like that. Okay, and so then it would be a binomial experiment. Okay, if we can, let me just say a little bit about that last part. I mean, there might be reasons why you wouldn't want to do that, but the reason that I point these things out to you that is just to say that this is one of the reasons why binomial experiments are so important to us, because you could almost make any experiment into a binomial experiment with a little bit of adjustment. And again, there might be reasons why you wouldn't want to do that in a particular case, but still, it's a very foundational distribution, the binomial distribution. So if you can identify that a distribution is binomial specifically, then we can do a lot with that information. We can calculate probabilities. We can calculate the mean and the standard deviation of the distribution a lot more easily than we could in the previous section. So let's go through all of that. Let's talk about computing binomial probabilities. So just as an example of this, let's say that x is the number of times we flip heads in 20 flips of a coin. X would be binomial here. And again, you might want to pause the video, make sure that it is, right? Make sure it satisfies all of those conditions, okay? But it is binomial. P is the probability of success in each trial. So in this case, P would be 50%, right? So if you ask somebody what's the probability of flipping heads, it would be 50%. But something like P of 7, capital P of 7, this is not the probability of 1 success in 1 flip. This is the probability of 7 successes in 20 flips. And so we're interested in computing probabilities like that. And that's much more complicated than trying to figure out what's the probability of 1 success in 1 flip, right? Now, so you might think this, right? You might think, oh, well, I have 20 flips, and I'm trying to compute the probability that 7 of them end in heads, but that's not correct, okay? It's much more complicated than that, unfortunately. So let's talk about how to compute P of 7, right? Probability of getting exactly 7 successes. So this is the probability density function for a binomial variable, right? P of x is n choose x times p to the x times q to the n minus x, where again, P is the probability of success, Q is the probability of failure, N is the number of trials, okay? And X is the number of successes that you want. So for now, I'm going to ask you to take it on faith that this really is the correct formula. And at the end of the section, there's a little sketch of a proof. It's not like a full-blown proof, but it's kind of a sketch of a proof to get us, to convince us, right, that this is really the case. Okay, so let's practice just using that formula. Number 3 here says, we toss a fair coin 20 times. Find the probability of obtaining exactly 7 heads, in other words, P of 7. So using this formula, right, that we have up here, P of 7 would be n choose x. Now, n is 20 in this case, right, because we're going to toss the coin 20 times. So it's going to be 20, choose, x is 7, x is 7. Okay, so it's n choose x times p to the x. Now, this is a fair coin. It's a fair coin. So the probability of flipping heads, right, is 0.5, right? 0.5 to the 7th power. If p is 0.5, then q is also 0.5, because remember, q is 1 minus p, right? It's the complement of p. So it would be 0.5 to the 20 minus 7. Or if you prefer, you could just call that 13, right? You could say 20 minus 7 is 13. In any case, you can pop this into your calculator now and see what you get. So I'll let you kind of pause the video and work that out, and then I'm gonna give you my answer. Okay, so this should come out to approximately 0.0739. So, okay, so for part B, this time it says we toss a biased coin that turns up heads 60% of the time. We toss the coin 20 times, find the probability of obtaining exactly 7 heads. So this is very similar, right? Except this time the coin is biased. Whoops. 20, choose 7, times p. Probability of heads this time is 60% because it's a biased coin. That means the probability of failure is 40% because 1 minus 0.6 is 0.4 to the 13th. Right, 20 minus 7 is 13. Okay, so let's see what this is. Go ahead and pause the video and try it out. Okay, on this one, you should get about 0.0146. It makes sense that the probability decreased in this case because if the coin comes up heads 60% of the time, then you expect it to come up heads the majority of the time. And yet here we're computing the probability that x is 7, that we get heads less than half the time, right? So that should be a fairly unlikely scenario, and that's why the probability decreased, okay? It's not always going to decrease in a situation like that, but in this case, it makes sense that it did, right? Okay. Now, what if you wanted to know the probability that x is within some range of values? Like, what if we wanted to know probability x is between 8 and 13? This is a very common scenario and something that we would want to figure out. Well, what you would have to do is compute the probability of 8, probability of 9, probability of 10, and so forth, all the way up to 13, and then add those up, which would be a very time-consuming activity to perform. And very tedious, right? So we don't want to do it that way. What I'm going to show you is how to compute these probabilities in Desmos, okay? So we'll do this in Desmos. In fact, I really don't want you doing the probabilities this way. I gave you these examples to show you how to use this formula, because this formula is what Desmos is going to be using. But I really don't want you using it by hand. Just use Desmos. Just use Desmos, right? So let me give you some examples of that. So here's how this works in Desmos. First of all, you need to open up the graphing calculator in Desmos. So far, I think we've been using the scientific calculator in Desmos. I've shown you how to use the scientific calculator to do various things. But for this, we need to open up the graphing calculator. And this is the link that you can use to do that, or you could just type it into your address bar in your browser, right? You can go to desmos.com/calculator, and that'll open up the graphing calculator. The next thing that you're going to want to do is type in binomial dist, right? Binomial distribution. And then you can enter in a number for n, right, which is the number of successes, and a number for p. In other words, you don't want to actually literally type the letters n, comma, p. You want to type in the number of trials, whatever that is, and then comma, and then the number of successes, whatever that, or the probability of success, whatever that is, okay? And then there will be a couple other things that that you should do, and I'll show you how to do those. But to get the probabilities, this is important information, okay? You're going to have to enter the minimum and maximum values for the probabilities that you want. So if you have a situation like this where you want the probability x is between A and B, you'll enter A for the minimum and B for the maximum, right? Piece of cake. But if you have a situation where you want the probability x just equals A, that's a little trickier, but it's not too bad. You'll just enter A for both, the minimum and maximum, okay? If you want the probability x is less than or equal to A, then there is no lower bound, right? There's only an upper bound. So you'll type in A for the maximum, but you'll type in negative inft, right? That's not a typo. Those are the letters you should type, infty. And Desmos will turn it into an infinity sign, right? But that'll indicate that there's no lower bound. Okay. For the probability x is greater than or equal to A, you'll enter A for the minimum because A is your minimum value now, but you have no maximum, you have no upper bound, so you'll type in positive infty, right? Or just infty, and that'll turn into an infinity sign there. Finally, if you have strict inequalities like this, you'll have to turn them into inclusive inequalities, right? The probability x is less than A is equal to the probability x is less than or equal to A minus 1. All right, this is true for a discrete distribution like the binomial. So just to put some numbers to that, because I know it seems kind of confusing. If x is less than 7, strictly less than 7, then that means that x is less than or equal to 6, right? If you're dealing with a discrete variable like the binomial. Similarly, if x is greater than 9, strictly greater than 9, then that's equivalent to saying x is greater than or equal to 10, okay? When you're dealing with a discrete variable. This is different if the variable is continuous, and we'll talk about that when we get to the normal distribution in the next section. But let's practice with these facts now. Practice using the Desmos calculator. Number 4 here says, according to Experian Automotive, 35% of all car-owning households have a red car. If we take a random sample of 20 households, compute the probability of each of the following outcomes. And in part A, we want the probability exactly 5 have a red car. Okay, so we want the probability x equals 5. Note, first of all, that this is a binomial situation, right? You either have a red car or you don't. We'll use the binomial calculator, the binomial distribution in Desmos to do this. So in Desmos, we're going to type in, so I'm just going to try to show you some work here. But in Desmos, we're going to type in binomial dist, and then we want to put in n and p. N is the number of number of trials, which is 20 in this case, right? We have a random sample of 20 households. And p is the probability of success, in this case 35, since 35% of households have a red car. So the probability you have a red car is 35%. That has to be entered as a decimal, okay? And then you'll need to put in something for the lower bound. Or actually, what is it called? The minimum value, I think, is what they call it in Desmos. So we'll enter something for the minimum, and we'll enter something for the maximum. Since we're looking for the probability x equals 5, our minimum and maximum are both 5, right? They're both the same. So this is what we'll enter into Desmos. Let's go over to Desmos and see what we get. So if you come over here to desmos.com, there's an option to open the graphing calculator. You could click open graphing calculator or this button to open up the graphing calculator. And what I'm going to do now is in this little space where my cursor is currently blinking, I'm going to start to type binomial dist, and you know that you've spelled it right when it suddenly becomes kind of bold instead of italic, right? And then you'll open up a set of parentheses, and it's even giving you a hint. It's saying trials probability of success, or success probability, right? And in our case, number of trials was 20, and probability of success was 35%. So I'm putting those in. Now, you'll notice that over here, right, they're trying to graph something. It's hard to tell what it is, but if you click on the little magnifying glass with the plus sign in it, then it'll automatically zoom in to that distribution. And this gives us the PDF. If you click on the find cumulative probability, then it will start to add up the individual probabilities there in that distribution. We want the probability that x equals 5. So for my minimum value, I'm going to type in 5. And for my maximum value, I'm going to type in 5. And you'll notice that in the graph now, it only highlights the bar representing 5, which is good because that's the probability you're looking for. And the answer is given in the little gray box, right? It's 0.127199, etc. We'll round this to 4 decimal places, so it's approximately 0.1272. So 0.1272. And that's our answer. I would like for you to show me this work when you do these problems, so that if you get it wrong, I can still award you some partial credit, right? If you just write down a wrong number, then that's not going to do you any good, right? You're just going to get 0 for that problem. In fact, I also want you to write out the full probability statement, not just the answer, right? So give me this entire statement and then show me the work as well when you're doing these kinds of problems. Okay, let's do another one. Part B asks for the probability that between 8 to 10 have a red car. So this is going to be probability that x is between 8 and 10. Again, we're going to use the binomial distribution in Desmos. So I'm just going to say it's the same thing here, but I do need to change my min and max. My minimum this time is going to be 8, and my maximum is going to be 10. So I'm changing my minimum to 8, changing my maximum to 10. And you can see again, it's highlighting those 3 bars, 8, 9, and 10, and it's adding them up for us. So that's about 0.3458. Okay. In part C, we want the probability that at least 2 have a red car. Well, if at least 2 have a red car, that means 2 or more, right? So this would be the probability x is greater than or equal to 2. So again, I'm going to be using the Desmos calculator. I just need to change the min and the max. It looks like 2 will be my minimum, but I don't have a maximum. There's no upper bound, so I'm just going to type in inft, right? And it should turn into an infinity sign when I do that. So let's take a look. Minimum we said should be 2. Maximum we said we should do int. And if I've done that right, then it turns into an infinity symbol, and you'll see it's highlighting all of the bars from 2 onward. Okay, so that comes out to about 0.9979. Now let's contrast that with part D, right? So for part D, we want the probability that x is more than 2. More than 2 have a red car, so strictly greater than 2. Obviously, if I just leave my minimum value at 2 in the Desmos calculator, this is going to be incorrect because this is the probability x is greater than or equal to 2. I don't want to include that 2, and so I should change my minimum value to 3, okay? Now this is the probability that x is strictly greater than 2. And you'll notice that it is the same thing as the probability that x is greater than or equal to 3, right? But we would say this is 0.9879. Actually, let me just say, yeah, you could say that this is equal to probability that x is greater than or equal to 3. Okay, which is 0. What did I say? 9879, is that right? Yep, 0.9879. And for this one, we put our min at 3, and our max, we still had infinity as our maximum. Okay, so that's how that one would work. Part E asks for the probability that at most 4 have a red car. At most 4. So that would mean 4 or less, right? So this is the probability x is less than or equal to 4. So we want the probability x is less than or equal to 4. That means that 4 is our maximum value. Okay, we're not going to get beyond that. Our minimum value, on the other hand, we don't have a lower bound, so we would just say negative infinity, right? And again, you'll see it's highlighting the bars that are less than or equal to 4, which is exactly what we want. So that's 0.1182. 0.1182. And for this one, we put our minimum at negative infinity, and we put our maximum at 4. Actually, for the negative infinity, what we actually typed was INFTY, right? Okay, and then finally, probability x is strictly less than 4. Whoops, strictly less than 4. Well, then we shouldn't include 4, right? We should just have 3, 2, 1, 0. So this is the same thing as the probability x is less than or equal to 3. So our minimum is again going to be negative infinity, but our maximum is going to be 3 this time. Okay. So let's change that maximum to 3. That's about 0.0444. Okay. So this is how we use the Desmos calculator to perform these kinds of calculations. Let's talk about how to compute the mean and the standard deviation. So as far as the shape is concerned, the shape of the distribution is actually going to change depending on n and p. Let me just show you that. Here we had a fairly bell-shaped distribution because n was somewhat large. If I had, let me get rid of this cumulative thing. If I had, if n was 10 instead of 20, okay, then yeah, you'll notice that this is not quite as bell-shaped as the previous one. Or if our probability of success was 0.15, right, again, it's kind of a skewed distribution now rather than a symmetric one. But as n gets large and as p gets close to 0.5, right, if I make p 0.5, well, now it's symmetric, right? If p gets bigger than that, then it's not symmetric anymore. Now it's right skewed. Okay? But if I make n large, if I make n 100, okay, then suddenly it's roughly symmetric again. Okay? So anyway, the idea is that the distribution of p is going to the distribution of x, right, of our binomial variable is going to change depending on n and p. But generally, as n gets large and or as p gets closer to 0.5, the distribution becomes bell-shaped. And for that reason, we'll use the mean and the standard deviation to describe the center and spread. You may remember from the previous section that the mean is the same as the expected value, and for a discrete variable, it's the sum of x times p of x. Well, we now know that p of x is n choose x times p to the x times q to the n minus x. So if you make that replacement, right, if you replace p of x here with the formula, the PDF, and then you do a bunch of simplification, right, a bunch of algebra that I'm not going to go over, then you just get n times p, right? It simplifies really nicely. Instead of having to use this nasty thing that sometimes takes a long time to compute, we can just do n times p, right? The number of trials times the probability of success. So it's very nice. If you want to see all of these steps, then you can watch this video. But I think it makes intuitive sense that if you have n trials and each trial has a probability of success p, then you would expect n times p successes. For example, if 25% of households, American households, have a dog as a pet, right? 25% of households have a dog, and you survey, let's say 100 households, right? Then out of those 100 households, you would expect 25 of them to own a dog, right? 0.25 times 100 is 25. So it's n times p. Okay. Similarly, right, for a discrete variable, this is the standard deviation, generally speaking. But if we replace p of x with its formula, then we can do some algebra and get a simpler version of the standard deviation. This is very nice, right? We just have to do n times p times q and then take the square root. So it's super easy, right? And here are those same facts just in a summary, okay? Let's practice. So number 5 here says, according to Experian Automotive, 35% of all households have a red car. Suppose that 400 people are sampled, and let x be the number of people with a red car. So then x is binomial, right? Because either you have a red car or you don't. Part A says, what number of households in this sample would you expect to own a red car? Well, that would just be the expected value of x, right? The expected value for a binomial variable is n times p. Okay, so that's going to be 400, right? We had 400 people in our sample times 35%, right? Probability of success. So you can punch that into your calculator and see what you get. Go ahead and pause the video and try that out. But you should get 140. So we expect 140 people in our sample to have a red car. Part B asks us to compute sigma sub x. By the way, the expected value is the same as the mean, mu sub x, right? Sigma sub x, the standard deviation of our random variable x, is the square root of n times p times q, which in this case would be n is 400, okay? P is 0.35. Q is 1 minus p, right? The probability of success is 35%. That means the probability of failure is 65%. Okay, so 0.65 there. And we'll type that into our calculator. And we should get something like 9.54-ish if we round to 2 decimal places. I hope you can appreciate how much easier it is to compute the mean and the standard deviation using these shortcut formulas than it is to use these nastier formulas that we had in the previous section. And that's because we have more information now. If the variable is binomial, then we get these shortcuts. And let me just emphasize that if the variable is not binomial, then you cannot use these shortcuts. These shortcuts only apply if the variable is binomial. Okay. So that's all I really have to say about the binomial variable. This last page is just some bonus information. This is the the derivation of the binomial PDF. So remember back on page 2, when I gave you this formula, I said on the last page we would kind of give a sketch of the proof, and that's what this last page is. I'm not going to sit here and read this last page to you, but let me just point out some things that I think are interesting, right? So to try to see why we get the formula that we get, let's look at an example, right? So suppose the probability of success in a binomial experiment is P, and the probability of failure is Q. A sample size of 4 is obtained, so n equals 4, and the number of successes, x, is counted. We're asked to construct a probability distribution for x. Okay, so first of all, note that since our sample size is 4, x can be anything between 0 and 4. So we can start off trying to find what's the probability x equals 0. All right, and that one's actually not too bad, because the probability x equals 0 is probability of f, so here I'm using capital F to represent failure, right? So it would be the probability of failure and failure and failure and failure, okay? Now, x is binomial, which means each trial is independent. That was condition 2 in that list of conditions, okay? So that means that probability of f and f and f and f, all of those ands just turn into multiplication. So this is probability of f times probability of f times probability of f times probability of f. Each of those probabilities of failure is just equal to q, right? So this ends up being q to the 4th power. Now, if we move forward and we try to find the probability x equals 1, then things get a little bit more involved, because now, in order for x to equal 1, we have to get exactly 1 success and 3 failures. That could happen if we get a success first, followed by 3 failures, or if we get a failure and then a success and then 2 more failures, or failure, failure, success, failure, or failure, 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 success. Now, note that each of those outcomes, this outcome and this outcome, they're mutually exclusive. In other words, if you had success first and then 3 failures, it cannot simultaneously be the case that you got a failure first and then a success and then 2 more failures. It's just not possible. Those outcomes are mutually exclusive. So each of these ors turns into a plus sign, right? So I just like this because all of that work that we did, learning about sort of the basics of probability, they all come into play here, right? So we've got independent events. We've got, first of all, mutually exclusive events, so those turn into the plus signs. And then we've got the independent events, and those turn into multiplications, right? So anyway, this just ends up being probability of success, P, times probability of failure, Q, 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 right? Q, P, Q, 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 P, and Q, and then P, 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 Q. Ooh, that one's wrong, actually. This one should be Q, 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 P. I'm kind of glad we did go through this. But anyway, so that means we have 1 success and 3, we have 1 P and 3 Qs each time, right? So we could encode each of these as P, right? Because multiplication is commutative. So you can do these multiplications in any order you want. So we could just call this P to the 1st power times Q to the 3rd power. And this one would also be P to the 1st power times Q to the 3rd power. And this one would also be that. So what we have is 4 copies of the same thing. Okay, so cutting to the chase. The moral of the story is this. If you want a certain number of successes, let's say X successes, then you need to figure out out of the 4 options, right? You need to figure out the number of ways that you can get X successes, right? And that's exactly what 4 choose X does. All right, so going all the way back to 2.1, right? That's exactly what 4 choose X does. It says out of our 4 options, we're going to choose X successes. That's the number of ways that this can happen. And then we're going to multiply that times P, the probability of success, raised to the number of successes that we want. And then we're going to multiply that times q, the probability of failure, raised to the number of failures that we want, right? And that's what the binomial distribution formula is telling us, okay? So I'll let you read through the rest of it and kind of think through the rest of it in detail if you're interested. But that's the idea. That's where the PDF for the binomial distribution comes from, right? So that'll do it for this section. I'll check in with you on the next one.